Hello students, today we can have a very small lecture having a very familiar topic which is ideal gases. The main features of ideal gas are: it is a theoretical gas or an imaginary gas. It is composed of non-interacting point-like particles. It always obeys the gas laws, and it follows kinetic theory of gases. Next we discuss how we will derive an equation for ideal gas. Let us consider a system of gas having a definite pressure. The volume be V, the temperature T, and N be the number of moles of gas. According to Boyle's law, at constant number of moles and temperature, the volume is inversely proportional to pressure. By Charles' law, at constant number of moles and pressure, volume is directly proportional to temperature, and by Avogadro's law, at constant temperature and pressure, volume will be proportional to number of moles of gas. By combining these three laws, we will get V proportional to N into T by P. If we change the proportionality constant by universal gas constant R, we will get the equation PV equal to nRT, which is ideal gas equation. Then we look what is the significance of this ideal gas equation. This law, ideal gas equation, calculates the behavior of any gas under common conditions of temperature and pressure. In the next section, we will discuss the deviation from ideal behavior of gases. Thank you.
Hi students. Along with ideal gases, I am discussing some more about molecular collisions. Kinetic theory of gases treats molecules as point masses and undergo constant elastic collision with each other and with the walls of the container. If we are modeling the molecules as hard, non-interacting spheres of diameter d, we can satisfactorily account for its various collision properties. First one is the collision diameter. When two gas molecules approach each other for collision, the distance between the centers of them at the point of their closest approach is known as collision diameter and is denoted by d. Hence, collision diameter is the distance between the centers of gas molecules at the point of their closest approach. Next is the collision number. In a gas, the number of molecules with which a single molecule will collide per unit time is given by the expression Z equal to root 2 pi d square C bar into rho, where d you know the collision diameter, C bar is the average velocity of the molecules, rho is the number density, that is the number of molecules per unit volume of the gas, and pi d square, it is the cross section of the molecule, because it is the cross sectional area of an imaginary sphere surrounding the molecule, as the molecule is considered as a hard sphere to which another molecule cannot penetrate. Hence, this expression gives the definition of collision number as the number of collisions suffered by a single molecule per unit time per unit volume of the gas. Its expression is very important. Next term is the collision frequency. It is by definition the number of molecular collisions occurring between molecules per unit time per unit volume of the gas. It is the number of molecular collisions. If you understand the equation for collision number, we can easily get an equation for collision frequency also. That is, collision number is the number of collisions suffered by a single molecule. Since each collision involves two molecules, the total number of molecules colliding per unit time per unit volume will be root 2 pi d square C bar into rho square. That is collision between two molecules. For more clarity, if we are taking two types of molecules, that is for a nitric oxide system, NO. N is the, rho 1 is the number density of N and rho 2 is the number density of O. Then Z will be root 2 pi d square C bar into rho 1 rho 2. Two molecules undergo collisions. Also, since each collision involves two molecules, it readily follows that the number of collisions of two molecules per unit time per unit volume will be half of the collision number. That is, for one collision, two molecules are involved. Hence, the expression for collision frequency will be 1 by root 2 pi d square C bar rho 1 into rho 2. Z12 is the collision frequency between two types of molecules. If it is same type of molecule, it will be 1 by root 2 pi d square C bar rho square. Z11. Next is the term mean free path. It is a very important quantity regarding gases and is defined as the mean distance travelled by a gas molecule between two successive collisions. That is, for a gas molecule, it travels some distance and collide with another molecule, travels some distance, collide and then collision. It is between two successive collisions, how much it travels. is the mean free path. For considering a molecule in a gas, we can, in a system of gases, we can calculate the mean free path of each gas. This by the expression lambda, it's the mean free path, and is equal to the average velocity of the molecule divided by the number of collisions suffered by it in the system. You may think, if at low pressure, what will be the mean free path of the gas molecule? That is, at low pressure, you can think easily that there will be less molecule or the molecule are far apart, and one molecule may take more time between two successive collisions. That is, its mean free path should increase if the pressure of the system decreases. What about collision frequency also? It will also get decreased. That is, the number of collisions occurring between two molecules. That will also decrease as the pressure decreases. Thus, I am giving you an assignment to prove how collision frequency will be proportional to pressure of gas and mean free path is inversely proportional to pressure of gas. We can easily understand it physically, as I said earlier, but we have to prove it through their corresponding equations, and I am assigning it to you. When I am assigning it, I will give you some hints also to help you, make you to work out the problem easily. Thank you, dears.